Hello IB, we're continuing on looking at our discrete probability distributions. Remember from last class we looked at our random variable, and we're calling it x, with a certain sample space, which means our x can be x1, x2 can be a range of values, and we get now a distribution of the probabilities when we have those different x values. So we're moving into looking more about a function here. We'll come to that in a moment. So the example we looked at was, say, tossing 2 coins, and we could make x our random variable. Let's call it this time x is the number of tails, just for a change. Could have done a number of heads, but make sure you look carefully at what you're defining as your random variable. So if we have the number of tails, and let's say we toss our coin, I don't know, let's toss it 4 times. So n is 4, the number of times we're tossing it. So x can be, will be anything from no tails, 1 tail, 2 tails, 3 tails, up to 4 tails. So the probability for any of these outcomes is obviously going to be between 0 and 1. So that's the probability I. I in this case could be 1, 2, 3, 4, well not 5, but that's our term numbers. The sum of the probabilities will equal 1, so the chance of getting all those probabilities will always add up to 1. So this is just putting that notation back in. So we're adding the probabilities from 1 to n, from first term up to the 5th term. That's going to be confusing because our n is 4. Alright, so just we'll have to be careful with that. We'll have to think about that carefully. Alright, I've just had a quick think on that. Basically, this is a generic or general form to say that we have n different values in our sample space, whereas here we're taking n as a specific situation in tossing a coin, where we can actually have 0 as one of our options. So there's 5 options when we have 4 tosses of a coin. So this n is not necessarily matching that n. So the same story down here. This formula here is matching our generic or general expression, where we're getting 1 to n terms, as opposed to this particular experiment. All right, so mixing up of our parameters here makes it confusing. So if this was an IA, this would not be a good state. I'd need to clarify it more, or use a different term. All right, so our probability distribution can be shown in a table with, like tossing our coin we did in 23A, or a graph. We can also talk about this functional form. So just like we've talked about our input of our different x's, our different terms, we have a probability distribution function, and that's often abbreviated to PDF, which is not the same as our PDF file for documents, which is a portable document file, I think. A probability distribution function is also abbreviated PDF. We also can refer to it as a probability mass function, and we'll look at more of that later, why it's that sort of concept to do with integration and the area under a curve. So our function notation, P is a function of x. X can vary. Our domain for the function are all the possible values of x being considered. So we could consider where our x is equal to 2, or we could have a range of values. But note the endpoints here are quite significant. So we now need to look carefully whether we've got an equal, less than or equal to's, or just a less than. All right, so that will be significant. Let's look at this quick example here. You've got a magazine store selling a whole lot of magazines to people. They've recorded how many they purchase. So they found that 23% purchased 1 magazine, 38% purchased 2, etc. So what's the random variable? The random variable is the number of magazines that are sold or purchased by a customer. So that's our x. Make a probability table for this variable. So we found that they could buy 1 up to 5, where 5% purchase 5 magazines. It doesn't make sense to include 0 because then they didn't buy any magazines, so it's not part of our probability. Unless you surveyed all customers, you'd have to then put a percentage of who didn't buy any magazines, but this was a particular emphasis on the data. So if one magazine is 23%, so turning that into a decimal, so we usually work in decimals with our probabilities of 0.23, the 38% is 0.38, etc. And we could show that with one of those spike graphs. And remember, we don't have it continuous, it's not a line graph, because the data is not continuous, it's discrete data. Here we have a formula for our probability. So here's a rule that says we can work out the probability when x are these numbers. We want to show that this is a probability distribution function, which means it's a function so that for this domain, it overall must equal 1, because our sum of our probabilities will always equal 1. So does this produce values which will add up to 1? So to test it, or to show that, we want to then do the probability when x is equal to our first one, which is 1. So 1 squared plus 1 over 34 equals 2 on 34. We go then and keep substituting in the rest. So why don't you pause the video at this point and have a go at filling in the rest of them. All right, how did you go working those out? Simple fractions, and we find that if we add up all those probabilities, we end up with 34 out of 34, which is 1. So we have shown that this really is a probability distribution function for a particular experiment, whatever that might be. So we could say, well, then what is the probability of x is greater than or equal to 3? So that means we want these values here. What's the chance of getting x is greater than or equal to 3? Will be 10 over 34 plus, that's a 4, plus 17 over 34 equals 27 over 34. All right, so we can just work out the probabilities that way. In this example here, the second one is showing that this is a probability distribution function. Hopefully you look at that and go, oh, I've seen that before. Yes, it's binomial distributions. So we're going to tie our binomial distributions into here. And I knew that would be really exciting for you. So here's our function. It's a probability based on x. Our x has these possible values, 0, 1, 2, 3. And in our binomial distribution, remember that was our n value up here, and this was our r value. So here's our r equal to 0, r equal to 1, r equal to 2, r equal to 3. All right? So that should be looking familiar. So if we want to show that this is a probability distribution function, then we want to calculate probability of 0, probability of 1, etc., and show that the probabilities all add up. So our first one's going to be 3C0, 0.6. Our x value is 0, and 0.4 to 3 minus 0, and then put that into your calculator, and let me check on that. I should be able to do that one in my head if I was thinking, because that's 1 That's 1.4 cubed is 4 times 4 times 4, which is 64, with 3 decimal places, so 0.064. All right, so go through and have a go at finishing those off, and we'll have a look at that in class to see how you go with remembering your binomial. The last one I just want to have a look at here, and we've got a bag containing marbles, 4 red and 2 blue marbles. 2 marbles are randomly selected. X denotes the number of reds selected. So there's our definition of our variable. So how many reds? So find the probability distribution. So do your tree diagram again, taking 1 marble, then taking a second marble. Write out your sample space. Do your probabilities, so multiplying along the line, remember. So here it's probably helpful not to cancel things down, though we could have cancelled all those down to 2/3 and 1/3. So now, if we want to do our distribution, here we've got our variable is red selected. So in other words, if we get 2 reds, that means x is equal to 2. Here we have 1 red, so x is equal to 1. No reds, x is equal to 0. So our probability here is going to be 2 out of 30 from multiplying those. Probability of getting 1 red will be these 2 added together, making 16 out of 30. And getting 2 reds will be that multiplied together, so we're getting 12 out of 30. That can be plotted up. So fairly straightforward, but you can see how we're starting to tie all the probability in. We can also see how there are discrete possibilities. We can only have no reds, 1 red or 2 reds. We can't get 1.5 reds. This one here, which we'll just have a look at and then finish in class, you might want to try and work through this, but we will go through this one in the lesson. So we've got a pair of dice being rolled. D denotes the sum of the top of the faces. So there is our definition of our random variable. So it's not x in this case. We've normally used x. Here we're using D. So when we look at our probability notation, we're getting the probability of D equal to 7 or D greater than equal to 7. So display your results in a table. So set up your table, get all the results set up. Then you can find the probability where the sum is equal to 7. And then find the probability distribution of D. So that means come up with your table and think, well, what's the lowest sum, what's the greatest sum, and do your distribution. And now when we look at this, hopefully that's ringing a bell. We've got a conditional probability. We're saying, what's the chance that D is greater than equal to 8, given that the sum is greater than equal to 6. So tying back all the probability that we did at the beginning of the year. So have a go with those, and hopefully you made some notes on that and try and work through some of these examples ready for class. Thanks for listening, and we'll see you in the lesson.